A friend of mine sent me this meme or whatever joke. It's pretty funny. So in the 1980s, A&W tried to compete with McDonald's quarter pounder by selling a third-pound burger at a lower cost. The production failed because most customers thought a quarter pounder was bigger than a third pounder. This is why I don't argue online. That's what makes the joke. I like it. We live in an era where you can find any fact you want to support anything you want. That was always true in the past too, but it was harder. You had to go to the library and dig through a bunch of books of facts to find the fact that you want. Now you could just Google it and find it instantly. Whatever fact you want, you'll find. All right, so we'll start with the intro and then chapter 2, reactivity. We'll continue. And as always, click back through these. It's a good thing, these outlines, to help you see what's going on, get prepared. So this is a repeat. You can get extra credit by telling me about yourself. Come to my office hour or break in lab and tell me your major, your career goal, something interesting about you, get an extra credit point. Also, you can earn some, you can use the EDMR at IR during our office hours, during my office hours, and before my first lab sections. So like Monday, Wednesday from like 1:30 to 2. I said 1:30 to 2 here. I think I said 1 to 2 later in this outline, but well, you come today around 1, you get if you want. And then Tuesday, Thursday before that first lab section. And my office hours have not been that popular, like I said before. So come get some more extra credit, get up to 3 points. Some of the most difficult NMR predictions you'll make are the ones that involve benzene. So I have a Google slide animation to help you with that. So this one, if you start on like slides 24, you can click through to 48. I don't think it's too many clicks, but that'll kind of get you going. And then this one teaches you how to do that, to make those predictions the way I want you to. It really makes you focus in on like atoms placements in a molecule and how many bonds away they are from other atoms. And it seems like I'm just being like crazy nitpicky on this, but I've noticed since I've gotten nitpicky about this and when I teach it, then the rest of the semester and the rest of the year goes really well because students get really good at looking at molecules carefully and in detail. So when they learn about reactions of them and things, it's a lot easier. And exam 1 is next week in lab on Wednesday and Thursday. I'll try to write an exam that takes the average student about 1.5 hours to finish, but I like to give you more time. I'm not opposed to you having like as much time as you want, because I think when you're taking an exam, it's some of your most focused learning. So you're not distracted by whatever's going on in your life when you're in the exam room, your phone's away from you and everything, and you're just working away. So if you spend like 2 hours on an exam, I think that's a good 2 hours learning, versus if you spend 1 hour on an exam, you only had half as much of that learning time. So I don't mind giving you extra time. So that's why in lab, we have 3-hour lab sections. So you have 3 hours there, and I'll give you a little extra time. Like if you want to start early, you can. So the Wednesday lab students, you can come in at 1 p.m. Lab normally starts at 2. Don't feel you have to come in at 1 p.m. because even when you come in at 2, you have like 3 hours to do it. And then Thursday lab people at 10:45 lab can come an hour early. And then the 2 p.m. lab people on Thursday, they can come in an hour early. But you'll be coming in and there may be some people from 10:45 still there. So just come in quietly and we'll find you a spot. And there's a question, but I just wanted to finish this. Place your cell phone at the front of the class before you start the exam, and no notes for the exam. Just bring your writing utensils and exam away. And there was a question, I think. I saw there was a hand raised. Sam, you have a hand raised. What's up?
Oh, sorry, that was my cat. He stepped on my computer.
That's funny.
I didn't mean to do that. Sorry.
Does your cat want a treat?
Yeah.
Great.
I actually had a quick question.
Is it for you or your cat?
Colored pencils or anything?
Is that for you or your cat?
Alex now.
Alex, is that for you or your cat? The question. Just kidding. I was trying to be funny. So Alex, yeah. So yeah, bring colored pencils and a pencil.
Okay.
But if you don't, I have them, so you can borrow some. And I'll put and then Alina had a question about periodic tables. I'll put a periodic table on the exam, like usually the first page of the exam has a periodic table, and there'll be periodic tables. Actually, I won't even do that. No, I'll save the paper. There's periodic tables up on the wall in lab. So, and I have paper periodic tables I can hand out to you as well. The periodic tables, it's a little bit helpful for like knowing the valence electron count, like, oh, boron's got 3 valence electrons, carbon's got 4. But, and then I guess electronegativity too, fluorines. So yeah, I'll give you a periodic table. So you don't need to bring one. I prefer don't bring one, because like, I'm not saying you would, but someone might like to try to cheat and put notes on their periodic table they brought, so let's not do that. And then next, the exams next week. So, sorry, I got my Zoom's got too many things in the way here. The material, that's for exam 1. So we'll cover all of chapter 1 and some of chapter 2. At this point, I'm thinking outcomes 1 to 11 in chapter 2, but I'll let you know, I might make it less than that. I might take out outcome 11. We'll see how far I get. I'd like to get through, if I get through all of the outcomes 1 through 11 today and in Monday's lecture, then I think I'll do it, all those. But if I get through less, if I'm like, this is going to be long enough without that, then I might cut it back, you know, an outcome or 2. But so I'll let you know more. And then of course, here's the lecture outcomes link there. You can see what I mean by that. So if I won't put anything on the exam that's not in the outcomes, or also, but I will put one other thing that's in the it's later in the outcomes, but you've been doing it in the lab. I'm going to do a spectroscopy problem as well, but I'll give you more details about that now. So some key topics though that I want you to know on the exam, that so you should know these are coming. It should be pretty obvious because we spent a lot of time on them. Or like, of course, the basic foundation, the bond line structures, formal charges, and octets. So I want to always put formal charges, and I'll be real nitpicky about that. Try to always remember to don't forget your formal charges. And octet idea, yeah. And then curved arrow mechanisms. I'll have a curved arrow mechanism question on there for sure. Multiple, so probably have an acid base. Probably have a couple at least curved arrow mechanism questions. And I'll want you to use colored pens or pencils for the reacting electrons. And hybridization, you got to know your hybridizations and their geometries, because you'll use them in your sigma and pi bonding diagram. So I'll definitely have a sigma and pi bonding diagram question, and it'll have the allene motif because I like that one. And if you Google search, I Google searched allene and I got this hit. Look at that. This is the classic. The allene's got the structure where one side the hydrogens are wedged dashed in the plane of the page. And it's because of their p orbitals that need to be used with the sp2 hybrid carbon, the sp in the middle, sp2. Here's the p orbitals like fully melded together type drawing. Okay, so we've been practicing that, so practice more. I had the Monday and Tuesday labs, you had a exit question with an allene motif in it. So if you haven't done that one, do it and have me check it at some point if you want. See if you made little errors and fix them before you get the exam question. And then and we'll have an energy versus reaction coordinate diagram question. I haven't shown you this yet, but I'm hoping to show you it either today or Monday in lecture. And a pKa using pKa's to predict acid-base reactions if they're product or reactant favored, and calculate the K equilibrium for that reaction. I'll be doing we've already talked about pKa's, but today I'll be telling you about how you can use that to predict if a reaction is product or reactant favored. And then alkane nomenclature. So we're going to learn nomenclature throughout the whole year, and we're going to learn by functional group. So initially we'll learn about just alkanes, and then we'll learn about cycloalkanes, and then alcohols next, I think. So we'll be, but for this first exam, I'll just have the alkane nomenclature, which I'll go over today or tomorrow. But if I don't get to it today, not tomorrow, but today or Monday, but if I don't get to it on Monday, I probably won't put it on the exam one. All right, and then spectroscopy, multiple spectrum problems. I'm going to put one of these on there, and I'll show you how I'll format it. And but I'm going to show you that at the very end of this lecture outline, because it just fits better to flow into the lecture. Experiment updates, the long spectroscopy intro NMR assignment. I'm getting more and more of those turned in. It was due on Monday. And I know that one took a long time, and it kind of makes me sad because I'm like, I was excited about it. I wanted it to be this perfect, great thing for you all. But then I noticed some people are like, whoa, this is a lot. So I'm like, it's going to be a lot of work. But I think next year I'm going to take out some of the more intense portions of this spectroscopy intro and then save it for a later separate assignment. I think it would work better that way. But yeah, it's going to be a lot of work to change it because that changes all the question numbers and the welcome backs and all that stuff. So I'll figure it out. But that's okay. I know this was a long haul, but getting through it, it's going to help a lot for the rest of the year. And then, so get that to me by Friday for no point loss, but finish it before then if you can. And then NMR and IR workshop is due this Friday. So this will have problems similar to like I'm going to have on the exam that I'll show you at the end of this outline. And then the determining of unknown structures with NMR and IR assignment, that one's not due till October because we have to wait till everybody gets a chance to get on the NMR and run the known samples, and then they're unknown. And then once you've run both known samples, toluene, ethyl and your unknown, you still can't really turn in your assignment yet because you have to wait for your partners to get you their unknowns. So it takes a little while, but it's okay. We'll start the solubility of organic compounds experiment this week. So Wednesday we have lab today, and so your pre-lab is try to get to question 14. I don't know exactly how long that'll take. Let me know how long it takes. If you don't quite to 14 because it's just takes a long time, that's okay. But show me what you get, and so I'll learn from it. And then Thursday we're not going to meet, so we're going to do the pre-lab the same though. Pretend like we're meeting. Do a pre-lab up to 14 if you can. And then this works out pretty good since we're going to miss lab on Thursday. A lot of this assignment, this experiment, you can do at home on your own. So that's good. So after you get to question 14, then question 15 requires you to be in person in lab. So you won't be able to do that, but you can skip to the video on page 28, which is cleaning up after an OChem experiment YouTube video. So you watch that video and then you come back to the document, the assignment, and you answer question 20 related to the video. Then you could skip to part C, testing for miscibility of two liquids on page 33. And you can read through that section and answer questions 24 to 28, because that doesn't require you to be in a lab. And then skip to part D, let's get charged, on page 49. And you can answer the questions 33 to 37. And then click through the Google slide animation on page 62 at the end of that part. And that's the Google slide animation. And so that'll keep you busy. If you can get through all that by the time we meet on Tuesday, you'll be doing great. That might be too much. So if you want, what you can do is just like after you've done the pre-lab or most of it, whatever, set a timer and see how far you can get in 3 hours. Because we have 3 hours of a lab you're missing. So see how much of this you can get through in 3 hours. And then if you can get through all of it, then when you come back into lab, you'll really know what's going on. You should be able to perform the experiment quickly and well. All right, so homework A, that's due now. Has a due date now. It's due today, I think, technically, yeah. But you could turn it in up to 4 days late. One problem with that assignment though is the Monday, Wednesday lab people, they can turn a paper copy in person today, right? Anybody can submit online whenever. But if you have a paper copy that you want to turn in Thursday when we don't have lab, then you can't turn it in until we meet next time Tuesday. Or if you're on campus, you can pop it in on a Monday in that Monday lab. But so I won't count it late if you're a paper copy person and you're turning it in next Tuesday. But that's actually more than 4 days from the due date, so that's fine. And then there's keys to that. You have the homework key there. And I'm going to try to do my best with have a normal office hour tomorrow, but I'll be driving down south at that time. So we'll see how good my cellular data is, the hotspot to my computer or to my iPad. So the office hour tomorrow is 9 to 10. And if Zoom is taking up too much, it's requiring too much cellular reception and I don't have it that well, then I'll just be on the Jamboard and I'll try to communicate via text and drawing there. So I think it'll work out. We can do it. If you ever have problems too with being in an office hour and you can't be on the Zoom. You can just get on the Jamboard and we could type back and forth to each other. And feel free to come to lab today. Again, I said this earlier, but if you want to run an NMR, so if you've already been through all the training, you can come in and you could run the ethyl acetate and/or, well, you don't, yeah, it doesn't matter which one you start with. Start with ethyl acetate and/or the toluene, get those going. My lab today starts at 2 p.m. But so even if you're a Tuesday, Thursday person, you can come from like before my Wednesday lab, 1 to 2. So is anybody that's here think they would like to come in today? At about 1 o'clock? Any takers?
I might, but don't hold me on that.
Okay, that's all right. So if you want, come on by. I'm here. Anyone else too? Stop on by. It's nice sometimes to be able to come if you have free time to jump on the NMR when no one else is around. And I just like the idea of us using it as much as we can. Okay, so we have a new SOTW. Cozy's reign has finally ended. A wildcat. We have a wildcat, a Whitney wildcat. A bio major will transfer to UCI, going to Irvine. UCI, of course, stands for under construction indefinitely. That campus keeps putting new buildings in constantly. And then we'll do research and development of vaccines. So that's a big, amazing field that's exploding now with the new pandemic vaccines. And played water polo and swam distance events, the 500 free in high school, at Whitney High School. And coach swimming in Auburn. Self-described nerd, likes to play D&D. And I wonder if this means they are good with the, like to see when we talk about the sp2 carbons are trigonal bipyramids, if it's easy for them to see it because, oh, I got the dye like that. That's the, what's a trigonal bipyramid? That's going to be 6-sided dye, but not the cube. But the octahedron dye, that'd be easier to see, huh? An Eagle Scout made a buddy bench for an elementary as part of his Eagle Scout work, and worked as an EMT at a scuba diving camp in the British Virgin Islands. That sounds awesome, huh? It mostly helped people with like jellyfish stings and ear infections. And our SOTW is Brandon Lee. Let's give a big round of applause to Brandon. Good job, Brandon. Let me see here. Let's see. Is Brandon here today? Are you on this one, Brandon? He might be watching it later. Yeah, I don't see him unless I'm missing. I got 16 here today. I don't see Brandon. All right, Brandon, well, congratulations when you watch this. And now, as I promised, I'll show you a problem like this, a spectroscopy type problem that'll be on the exam one. Here it is. So I'll give you a question. Pretty much, I think I'll just copy and paste these instructions, but I'm going to change the molecule out so you have a different molecular formula. So I'll give you spectra of a molecule with a molecular formula. This example is C3H6O2. And I want you to do the following. You'll calculate degrees of unsaturation for the molecular formula and show your calculation. So I'll demonstrate that with this, and I'll give you a little background on that because that was part of the spectroscopy intro. And then state all possible combinations of rings and pi bonds that can happen for that degrees of unsaturation, determine the structure of the molecule and draw it on all 3 spectra, number all the carbon signals from like most downfield to upfield, and then letter the proton NMR signals, and then give their predictions, circle your groups and predict, like we've been doing in the NMR training. And then in the IR, you'll draw arrows touching the bonds to the signals. And a few of you on the NMR and IR data quiz, you were mixing up NMR and IR. So remember, NMR is nuclear magnetic resonance. So you're looking at the nucleus of atoms. So you should circle atoms and say, oh, this nucleus, this carbon nucleus is causing a signal here. Whereas IR is talking about the covalent bonds between atoms, bending or stretching and bending, right? So when you're talking about IR, you should be like touching a bond and drawing it to its signal. Some students were saying things like, oh, in the proton NMR, it was the OH bond that caused the signal. That doesn't make sense because OH bond, that's IR. Proton NMR is the nucleus. Like NMR stands for nuclear magnetic resonance. All right, so let's move on. First, a quick review of data we should have memorized. Yeah, let's do this really quick. So IR spectroscopy. I'll go through these really quick here. So what causes this big mess on the chat? Someone tell me what's causing this. In the IR, around 3,500. Can't get the chat up. I don't know why. I guess no one's chatting anyway. So that is the carboxylic acid OH. There it is, right? So that's how I want you to label the spectra, touching the bond to the signal. And it's not the OC bond. I see that a lot. That's an error that's made. This strong one here is a carbonyl. So you touch the carbonyl bond to the carbonyl signal. What shows up around the same area as the carboxylic acid, but more parabolic. I usually get more response from people, but I'm getting nothing. I just want to make sure, is everybody, can everybody hear me?
Yeah, so are you not seeing the chat?
My chat's not working. Oh, there it was. Now it works. I guess I have to have it up before I go to the presentation mode. Oh, thank you, Ryan. Yeah, now I'm seeing it. Good. Now we're getting it. Yes. So we got, this is the OH of an alcohol. So it's that the bond between oxygen and hydrogen. There we go. Not the OC. Okay, now what about here around 3,000? What's to the left of 3,000? I saw one alkyne, not alkyne, but alkene. I might have just mistyped it. The alkene CH is what causes that one. There we go. So it's the carbon to hydrogen off an alkene, not the carbon-carbon double bond. It's the carbon-hydrogen. All right, just under 3,000. Alkane CH, good. Just to the right. Okay, not the carbon-carbon bond. And there's my old diagram. Carboxylic acid. Oh, alcohol, alkene, alkane, carbonyl. We got it. All right. So let's try the other one. Okay, proton NMR signals. What shows up around 12 parts per million? What's this red one covering up? Yes, carboxylic acids over here, right around 12. What shows up about 9.5, between 9 and 10? The aldehyde hydrogen, yep. Then what shows up between 7 and 8? Yeah, the aromatics, benzene rings. Between 5 and 6, kind of similar to the benzene rings, but different. The non-conjugated alkenes, just alkenes by themselves, not in a ring. Well, they could be in a ring, but they can't be in a ring where it's like double bond, single bond, double bond. All right, what about 3.84 parts per million? Alpha to the oxygen or nitrogen. Good. And then what about 2 parts per million? Alpha to the carbonyl. So that carbon that's directly attached to the carbonyl carbon, that's alpha to the carbonyl. And then its hydrogens are also considered alpha. And then most upfield, alkanes. Yep. And what about over a broad range because of hydrogen bonding from about 0.5 to 5? What can show up there? alcohols and amines, yeah. Good. Now, oh, that's it for the proton. Carbon. Oh, what shows up furthest downfield? 200 parts per million. Could be an aldehyde or ketone. It's the carbonyls that have atoms that have either hydrogens and carbons, but the hydrogen and carbon don't have lone pairs on them. Then next up, around 175-ish, the carbonyls that have atoms with a lone pair on it, so an ester, an acid, an amide. All right, now in carbon NMR, we have two groups that kind of are in the same region, where in proton NMR, they were separate. What two groups can show up around 100 to 160? Yeah, the alkenes and the aromatics, they both kind of overlap in this area, 100, 160. Then around 55, 60 parts per million, this yellow one, what's that covering up? Yeah, alpha to an oxygen or nitrogen. Then around 25, 30, sometimes even all the way down to 20. Alpha to the carbonyl. Yep, carbon directly attached to the carbonyl. And then most upfield, alkanes. All right, and then I have a last little thing. It shows how they're similar, the proton signals and the carbon signals. So like the most downfield on proton NMR is the carboxylic acid and the aldehyde, and these in carbon NMR, the most downfield are carbonyls, so that makes sense. And then carbon NMR, you have the aromatics and the alkenes kind of overlap, but in the proton NMR, the aromatics are downfield 7 and 8, alkenes are 5 and 6. Then they both have this same pattern, alpha to oxygen or nitrogen, alpha to oxygen or nitrogen, alpha to carbonyl, alpha to carbonyl, alkanes. And then proton NMR has, it doesn't have a signal for an alcohol it's already addressed for, and carbon doesn't have the signal for an alcohol that H off of the alcohol part. All right, good work. So now let's look at a problem. My next slide. Yeah, we're gonna do this one right here. Okay, so the first thing I'll show you is that the question about calculate the degrees of unsaturation. So the degrees of unsaturation formula is the following. Let me get my Jamboard going. So it's degrees of unsaturation. It's the number of carbon atoms plus 1 minus the number of hydrogens atoms plus halogens minus nitrogens, all divided by 2. There's other formulas you'll find online. People just rearrange this formula basically, and I like this one. You can use another formula if you like, but I'll use this one, and as long as you get the right degrees of unsaturation, you're good. So for our formula for this guy, it's going to be C is 3 plus 1 minus hydrogens. How many hydrogens we got? We got 6 hydrogens minus how many halogens, like fluorines, chlorines, bromines? We got 0 of those, minus how many nitrogens? Oh, it's actually plus halogens, minus nitrogens, 0, all divided by 2. So now this is a big, I'm going to give you a real good bit of advice right here. When you're doing this calculation, go slow. It's easy to make a little error where you just you mix up the plus and minus sign or something. In this case, it wouldn't matter because they're both 0, but if they were numbers like 1, 2, 3, you'll mix up these plus and minus signs, that'll mess you up. Or more often, you'll even just make a mistake and you're doing the calculation. So I'm going to do it really slow. 6 over 2, 4 minus 3 equals 1 degree of unsaturation. So if you take your time like that, you're less likely to make a mistake. If I made a mistake and I accidentally just I don't know, I said 6 divided by 3 was 2 for some reason, and now I have 2 degrees of unsaturation, it'll really throw you off on a problem like this. This kind of problem can take a little while. And if you have the wrong degrees of unsaturation to start, it just leads you down a bad path. So yeah, I don't try not to do that. And the X up here, a reminder here, the X equals a halogen, which is like fluorine or chlorine or bromine or iodide, one of the halogens. All right, so here we got it. We got 1 degree of unsaturation. What does that mean? That means we have either I can't spell either. I don't know why. EITHER. I'm so bad. We either have 1 pi bond or 1 ring. Both of those add up to a degree of unsaturation. So I just answered the next question, didn't I? It says, calculate degrees of unsaturation, state all possible combinations of rings and pi bonds for this molecule. Yep, I did it. Now I got to determine the structure. So let's look at this spectrum more carefully now. So what do we see? What jumps out at you first? Can anybody tell me when they look at these? Let's say we look at the IR first. What's the thing that jumps out at you right away? Yes, good. I see this is, it's kind of hard to read here, but that's 1500 centimeters, centimeters, so that's 16. So this looks like to be about 1750. So carbonyl. And then once I see in the IR, I've got a carbonyl. Where do I look next? And yes, Ryan, this does tell me I've got sp3 carbon hydrogens. But what do I look next for the carbonyl? I look at the carbon NMR, yeah, this right here. This seems to be at about 170 parts per million. What does that suggest? That suggests I've got not a ketone or aldehyde. Ketone or aldehyde's over here, huh? What I've got there is either like an ester, an acid, an amide, something with the resonance to the carbonyl. And then when I come over to the proton NMR, I look at this, I got 2 singlets, huh? And they have an equal amount of hydrogen. So wait, if I've got 6 hydrogens, what should my integration be for these? It looks like, oh yeah, that should be a 3 hydrogen singlet and a 3 hydrogen singlet, huh? Because they have to add up to 6. 3 and 3 make 6, and there's an even amount in both. Why is this signal taller, but the integration's the same? Anybody know? Well, if I have like a rectangle like this, and then another like more, can they be the same area? So this rectangle is taller. This one's wider and shorter. They could be the same area probably still, right? So that's why, like this one can be taller. This must be a wider signal. It's hard to see here, but it must be a little wider than that one. Okay, so I got that, and now I'm looking at a signal at about 3.8 parts per million. What does that suggest? And then another one here, about 57 parts per million. Alpha to oxygen or carbon, yeah. And I do have 2 oxygens here. So Do you think I have a carboxylic acid? I could have an acid or an ester maybe, huh? Do you think it's an acid? So if it's an acid, so if it's an acid, then this guy right here, that's a 1 hydrogen singlet. Oh, got messy. About 12 parts per million in the proton NMR, but do I have that? I don't have that, huh? So I think it's an ester. So let me try to draw out at like the beginning of an ester. Let's go. Ooh, ooh. So an ester needs an oxygen off the carbonyl and then a carbon there, right? So that's an ester. How many carbons total does this molecule have? 3, huh? How many did we just use? 1, 2. Oh, yeah, I think that's our ester. So, okay, I think we got it. But let's double check that. So the nice thing about these, the really nice thing about these problems is when you do get the correct answer, everything matches up well with the spectra. So let's do this. I'm going to number my carbon signals 1, 2, 3, and then I'm going to see if I can predict these properly. So this right here should be a signal that's alpha to a carbonyl. So it should show up around 25 or so. So I think that works out good with 3, huh? This is the carbonyl signal that should show up around 170 because it's got resonance. That works out perfect for signal 1. And then this one here is alpha to an oxygen, should be about 57 or so. It's 2. That looks perfect, huh? Let's go to the IR. We'll label the IR completely too. And when we label the IR, I want you to always draw out the bond that causes a signal and then touch that bond and then have with an arrow that touches the signal that causes it. So let me see. I'm going to draw on one of these hydrogens to represent these alkane signals. And I'm going to say, okay, touching that bond, it's causing this signal, which is just under 3000. Then the carbonyl signal is right there. 1700. Perfect. So I touch the bond, touch the signal. And I'm not a fan of like the circling of the thing, just touch the bond. I think it's cleaner. Also, I'm not a fan of drawing like fragments of a molecule. You draw like, you say, oh, this is an sp3 carbon hydrogen. You just draw like a CH and you say, that's it. Draw the actual molecule. And then the proton NMR, that's usually the most informative. So for this proton NMR, I have signal, I'm going to label my signals A and B because I use numbers for carbon, letters for proton, and then I'll predict. So I've got a 3 hydrogen singlet, which should show up about 2 parts per million because it's alpha to a carbonyl. So what is that, A or B? B. And then this one right here, this is another 3 hydrogen singlet, and it should show up around 4 parts per million. So that's obviously A. Awesome, right? But once you get the, if you can get the structure and when you go label it all like this, it makes it perfect for you. there was a question from Santos here. Could the alkane IR signal be from the oxygen? Yes. So I use this CH bond as a representative of all the hydrogen carbon bonds that cause this, but all three of these contribute to this, and all three of these CHs contribute to that too. Now I want you to do this with yes. And no, Ollie. Annalise, this is an exam type question. And then when I go back to the question, oh, so this is what I want you to do. So it's important to have good exam test taking techniques. So I'll tell you how I do an exam question. Let me get over to back to here. So what I do, this is how I try to be really careful with my exams questions, or just questions in general for anything. This is what I try to do. So first, I read the question. Pretty obvious, right? I usually just read it quickly. Then I reread it and underline or circle key things. After that, I answer the question. Then I'm not done there. After I've answered the question, I reread the question to make sure I answered all of it. This last part, 4, a lot of my students, they don't do that. And sadly, this will happen next week on the exam. And so they'll turn in the question that they knew how to answer all of, but they only answered maybe 80% of it. They didn't do the last part because they just forgot to, and they didn't reread it to make sure they did it. So be sure to do that. So let me demonstrate. I have my, the original question was here. Did I calculate the degrees of unsaturation? I did. Did I state possible combos? I did. I could see someone missing this. They got the degrees of unsaturation and they skip ahead. I drew the structure of the molecule on all 3 spectra. I numbered my carbon signals. I did. And on the molecule, I labeled my hydrogens. I predicted their coupling. I used the letters. And did I draw an arrow touching the covalent bonds to touching the, yep, I did it. So, okay, I feel happy. I've completed this question. Now I can move on to the next one. I had a question, did we do B? Yes, we did do B. It's right here. We either have 1 pi bond or 1 ring. So Annalise, when you are, oh yeah, Annalise, when you watch the video, you'll see. All right, so that's the intro, huh? There's a lot in that intro. That's good. Get us ready for the exam. Any more questions about that? Okay, so we'll get back to chapter 2 outcomes. So if you remember, when we got into chapter 2 outcomes, I said we're going to skip outcomes 1, 2, and 3 initially and start working on the acid-base stuff. So I want to get that through for sure. So you're ready for the quiz of it on. You'll have a quiz of this material on Monday, Tuesday, and then it'll also be on the exam on Wednesday, Thursday. So we did. We're going to review the pKa's. Okay. Let's do a quick review of these pKas. What did I say to start on? Slide 3. There we go. All right, so I want us to memorize some of the more important pKas. It really helps you, you'll see throughout the year. And this will be the last thing to memorize for a little bit in terms of just like straight numbers and things. But it's just part of the language. It's like knowing, if you can remember that the sound of the letter A and the sound of the letter B, then you can read. This is kind of like just learning our letters initially. So we have our very strong acid, sulfuric acid. It's extremely strong. Get it on your finger, get concentrated sulfuric acid on your screen, on your finger, and it starts burning you right away. So you don't want to touch that, but it's very strong. Its pKa is so strong, it's negative. So the lower the pKa, the stronger the acid. So sulfuric acid, pKa is about -10. That's what I call it. You could say, you look it up online and have different pKa, negative 12 or something. Here, let's look real quick. Let me get out of here. What's the pKa of sulfuric acid? So let's see what Wikipedia says. What? Sulfuric. Oh yeah, this makes sense. So the first one, oh, they're just going -2.8. They're going low. I don't know about that. So this is something that chemists will debate about too. They're like, what do you mean it's only -2.8? So let's see. Boundless chemistry. Let's see what Lumen says. Sulfuric acid, they're going -3. Sulfuric acid. I don't know about that. And then let's see what Chemistry Libre says. They're going -10 like me, sulfuric acid. And that's a big difference, huh? -3, -2 to -10. This is a log scale. So those are like a -3 to -10 pKa. That's a difference of 10 to the 7 zeros. So that's a 10 million different. But the reason why this happens is because sulfuric acid is such a strong acid. When you put it in water, it basically reacts completely. So we're really saying it's like in general chem, you say, oh, it's a strong acid, it just reacts completely. But if you want to compare two different strong acids that when you put them both in water and they react completely, how do you compare them? What you do is you put them in a different solvent than water, maybe like DMSO. That's a solvent we'll talk about more later. So you say you put these two really strong acids in water that basically react completely. You put them in a different solvent and you figure out who's stronger. And then you try to like make assumptions as their pKa of what it is in water, like coming from that other solvent. So the assumptions from one solvent back to water, chemists make different assumptions. That's why you see different pKa values for the really strong acids and base, and also for the really strong bases too. So let's see, pKa of sulfuric acid. Let's see what these people are saying. They're just going strong, so they don't even want to get in this debate. They don't want to put the pKa there. So, oh, it's just strong. So these are the values I'll have us remember. We'll go sulfuric acid -10, and we'll go hydrochloric -7. And I do believe sulfuric acid stronger than hydrochloric acid because it's pretty cool. You can take table salt, sodium chloride, which has the conjugate base of hydrochloric acid, chloride. And if you drip in concentrated sulfuric acid, the HCl gas will bubble out as a gas. So that's showing sulfuric acid could make hydrochloric, so it is stronger. Anyways, so we got the -7, and then the hydronium's -2-ish, and then acetic acid's about 5, ammonium, nitrogen with a plus charge is about 9, methanol, water, other alcohols, ethanol, other ones, they're all about 16. And then ammonia is very weak, 35. And the difference between ammonia and ammonium is ammonia just has 3 single bonds with the lone pair, where ammonium has 4 single bonds and a positive charge, no lone pair. And then methane is a representative alkane, 50. So it's super duper weak acid. We don't really use it as an acid, but we have ways to make its conjugate base but we don't even do it via acid-base chemistry. Okay, so we're going to memorize these. Let's practice. So sulfuric acid, what's the pKa of sulfuric acid? Oh, I got to bring up my chat. Sulfuric acid, good, -10. Hydrochloric acid, -7, good. Hydronium, 2. Oh, sorry, -2, -1.7 or about minus. Acetic acid, about 5. Ammonium, that one's the one that's about 9, the nitrogen involving one. Methanol and water, about 15, 16. Ammonia, this is the nitrogen with no positive charge and a lone pair, 35. And then the weakest of all, the alkanes like methane, 50. Awesome, good job. And then let's go backwards. What has a pKa of about -10? Sulfuric acid, good. What has a pKa of about -7? Hydrochloric acid, good, HCl. And then which one's -1.7 or around -2? Acetic acid. I mean, sorry, acetic acid, hydronium. And then around 5-ish is the acetic acid. And then around 9, ammonium, around 16, water, alcohols. And then 35, ammonia. And then 50, methane or alkanes. Cool. All right, so on the quiz that you're going to take, you're going to have to guess the pKa of things not exactly like this, but similar. Actually, I shouldn't have left my presentation. So it's going to be like this. So when you look at benzoic acid here, which of these above pKa's does it look most like? It's a carboxylic acid. So benzoic acid looks mostly like acetic acid. So its pKa should be about 5. Then here I've got a nitrogen with 4 bonds and a plus charge. What's that look mostly like? Looks mostly like an ammonium. So the plus charge of the nitrogen looks like ammonium. So its pKa you'd say is about 9. So knowing these 1, 2, 3, 4, 5, 6, 7, 8 pKs makes you able, it gives you the ability to predict thousands and thousands of pKs, things that are similar. So what about this one? We've got nitrogen with 3 bonds to it and a lone pair. (35). Weak acid. And now we have isopropyl alcohol, also called, it's part of rubbing alcohol. You might have at your house. So rubbing alcohol, it's an alcohol. So its pK should be about, methanol, should be in water, should be about 16. Now this, what about this bastard? Butane, the bastard gas. About 50. And now HCl, hydrochloric acid. What's its pKa? This one's, it's not like it's like HCl, it's exactly HCl, so it's a -7. And then a protonated ether. Oxygen with 3 single bonds, a lone pair, and a positive charge. That's most like hydronium. So it would be about -2. Okay, so you're gonna get a quiz like that, huh? Let's see. Oh yeah, this is the, now then we're gonna use this, these pKs, we're gonna predict reactivity with them. Before I do this example though, I think we should probably take a little break. We'll pause there. So let me set a timer. So any questions I can answer during this break? We'll take a 10-minute break. Yeah, there's the GSA for the acids and bases. It's this one here. I'll tell you what I'll do. It's, I'll show you where it is. So if I go to Google Sheets, we'll start at this spot. I'll get to your question just a second, Josephine. And if I go to animations, then I go to, where's pK? pK and acid base equilibrium is right here. That's the one I'm doing right now. So it'll step you through all that. It's part, oh, you know what? I think for some reason I don't have it in here. I meant to put it in here. Yeah, here it is. It's in our outcomes too, linked there. And I'll put it in chapter 2 homework as well. Okay. I saw 2 hands raised. Let's see whose hands raised. Josephine and Sammy. What's up, Josephine? You had a question about an NMR problem you're saying? Which one is that? Or do you have, what kind of NMR question do you have? So is it the, is your question, Josephine, from the NMR and IR workshop? So Josephine, while you're figuring out like which assignment and the question number, let me see if I can get to Sammy real quick. What was your question, Sammy?
So for the exam, I have accommodations. So am I gonna be taking it in the lab with?
Oh yeah, I was wondering about that. So do you know, is the testing center open? Because I emailed them at the beginning of the semester and I don't think they ever got back to me. It's weird.
I'm not entirely sure.
So can you look into that for me? And I'm completely fine with you taking it here if you're comfortable here in lab, you know. But if you can find that you could take it over there, I'm totally comfortable with you taking it there too. So
Okay.
just try to get you the best spot available.
Yeah. I'll find that out.
Okay, thanks, Sammy.
Mhm.
Oh, someone said the testing center is open, so that's good. So if you want to take in the testing center, you could take it there. Just let me know. So sometimes people have accommodations. They want to take it in the testing center, which is fine. Some people who have accommodations, they're like, oh no, I'll still take it in lab. So let me know so I don't walk over your test somewhere that's you're not going to be. Now oh yeah, I know where we're at. We were about to get into this using our pKa values we memorized to help us predict if an acid-base reaction is product favored or reactant favored. So let's go back. I'm going to do it on the Jamboard so that I don't know, just see it a little different way. So using pKa to predict if a reaction's product or reactant favors. L4, L4, 5. Okay. So this is pretty cool. If I pick an acid, so why don't you help me make up a problem? Someone say out loud or type in the text any type of acid that we've memorized. Okay, I got an HCl request. Hydrochloric acid. And let's have it react with something. Can someone name anything for it to react with? in an acid-base reaction. We'll go with water. And I'm going to color code this, and I'm going to be using curved arrows too. So here we go. So let's look at the reaction that could take place between these. The water could reach out a lone pair, and I'm touching the red lone pair, and then I'm touching the hydrogen it's reacting with, and it'll break the bond between the hydrogen and the chlorine, and I touch the bond between the hydrogen and chlorine, and I touch the chlorine. And what do I get? I get chloride. And I'll put a blue lone pair there to show that these two electrons came from the bond between C and chlorine and hydrogen. And then my water now is no longer water, it's hydronium. And it has a plus charge. And it was this red pair of electrons that became the bond between them. Okay, so does this reaction, what's your guess? Do you think this reaction would be product favored or reactant favored? So I'll show you a way to predict it. What you do is you find out what is the acid on the reactant side and what is the acid on the base side. So maybe I'll abbreviate it. I'll say reactant side acid. I'll put RSA there. Let's make this a little smaller too. So I'm going to find out what is the reactant on the reactant side. And then, so let's do that. So what is the acid over here? Is it the water or the hydrochloric acid? Yeah, it's the hydrochloric acid. So this is the reactant side acid, right? The water is acting as a base. It's deprotonating the acid. It's accepting a proton. It's a proton acceptor. That's a Bronsted-based definition. It's a Lewis base as well, because Lewis bases are electron donors. It's donating a pair of electrons to make the new bond. Okay, so after you've determined what is the reactant side acid, then your second step in this thing is to determine what is the acid on the product side. So if this reaction were to reverse, if I was going to have the chloride deprotonate the hydronium to send us back that way. So can you see this blue pair of electrons from the chloride, maybe taking away this proton, breaking the red bond? So in this process, who's the acid? Is it the chloride or is it the hydronium? It's the hydronium product side acid. Okay. After you've done that, then your third step is you have to ask yourself, which side has the stronger acid? Use pKa's. So what's the pKa of the reactant side acid, of the hydrochloric acid? -7, seen a bunch of them, that's good, -7. Then what's the pKa of the hydronium? About -2, -1.7 or -2 approximately. Okay, so which of those is stronger, the hydrochloric acid or the hydronium? So the hydrochloric acid has the lower pKa, so it's the stronger acid. I know the magnitude 7 is bigger than 2, but the sign is negative, so it's lower negative. It's lower pKa. Lower pKa, stronger acid. That got ugly. So if that's the stronger acid, then what do you think it is? Do you think this reaction is reactant favored or product favored? You want to think of it this way. The stronger acid will push the reaction to the other side of equilibrium. So if my hydrochloric acid's stronger, it's going to push the reaction to the right. It's going to make this a product favored reaction. This is a product favored reaction. Okay, and I want you to be able to just do this with practice. You're gonna be able to do this quickly. You'll just look at a reaction like this and you'll say, okay, I got -7, -2. Stronger acid, oh, it's gonna be product favored. I'm gonna have almost all chloride and hydronium. I'm gonna have almost none of this hydrochloric acid and water in this one because it's just product favored. So I could draw my arrows then, I can draw them with like, whoa, like almost all to the product side. And I also want you to do another thing, is to calculate the K equilibrium to say how much it's product favored. Is it like, I'm telling you already that this one's hugely product favored, but let's calculate to see how much. So to calculate the K equilibrium for this reaction, so there's a K equilibrium involved in here. And the K equilibrium, remember, it's products over reactants. Products over concentration of reactants. So there's a formula we're going to use, and it's not too hard. It's K equilibrium equals 10 to the product side acid pKa minus, I shouldn't put that minus right there. Product side acid, I'll do this, pKa minus the reactant side acid, pKa. Okay, so let's try this out. So for this one, it's 10 to the product side acid pKa. What's the product side acids pKa for this? It's right there, right? -2. And you could say -1.7, but -2 is good enough. So we got that, right? And then we're going to subtract. Let me put these in parentheses so the negatives don't get confused. So that's my product side acid. And then what's my reactant side acids pKa? -7. So what does this math work out to be? 10 to the -2 plus 7, it's actually 10 to the 5. And what this is telling us is that we get 10 to the 5. 10, what's that? 10 to the 5 would be 100,000 times more products. There's 100,000 times products to every one reactant. So that sounds pretty product favored to me. Okay, so let's look. Go back to my GSA here. This GSA has everything you need, but I like to show it worked out too the way I did. So let's try this one here. So we have benzoic acid and an amine, and we could see a curved arrow mechanism taking place. Oh, actually, I'm going to put the pKa's down here. So this is a good point. So we do learn that this amine can be an acid as well. Sometimes it can be deprotonated. But if we have these two reactants, benzoic acid and an amine, which one is more acidic? What's more acidic, this benzoic acid or this cyclic amine? So the benzoic acid's much more acidic, so that's going to act as the acid in this case. I'm not going to use my benzoic acid to deprotonate the amine. So draw some curved arrows for that. Boom, boom. Got a carboxylate here. It's called benzoate. And then I've got a protonated amine here. It's called, this is an ammonium. All right, now I could put pKa's by some of these too. We didn't memorize a pKa for a benzoate, but we do know it for a protonated amine, right? So does this look like a reactant or product favored reaction? So I'm going to do it on the Jamboard. Let's see what it says. Yeah, so this is our reactant side acid. It's getting deprotonated. And if we're going to revert, so yeah, this is a good point. So a lot of times students make an error. If they don't use the reactant side acid to predict things, they use the base's pKa. But this base, this is acting as a base, not an acid. It didn't get deprotonated. All right, so then now which on this side would be our product side acid? Would it be the ammonium or the carboxylate? Like, could you imagine a lone pair coming from the benzoate to deprotonate this? So which one's the acid? If we reverse this reaction, that would be the acid, right? Because it would be deprotonated. Okay, so compare them. Which is the stronger acid, benzoic acid or this ammonium? The benzoic acid is the stronger acid. And since that's the stronger acid, has lower pKa, it's going to push the reaction to be more towards the product side, right? So this is a product favored reaction. And how much is it product favored? Let's calculate the K equilibrium. So the formula is 10 to the product side pKa, the 9, minus the reactant side pKa, this guy's pKa. Make sure you use this one, not that one, because that's not the acid. So if we plug in our numbers, we get 10 to the 9 minus 5, it's 10 to the 4. So the reaction is very product favored. It's 10,000 times the ratio of products concentration to reactants. Is that making sense? So yeah, so you'll have this quiz next Monday and Tuesday, and it shouldn't be too bad. It's just, here's the quizzes actually. So not only do I give you the quizzes, this is like the the last quiz you did, this spectroscopy, the NMR and IR data quiz. I give you 1, 2, 3 quizzes. These are the 3 quizzes, one of which you'll get. And I also have the answer key. So let's try a little bit real quick. So like this one, what's the pKa of this first molecule here on the left? What's this pKa? It's not an alcohol.
Five.
This a carboxylic acid, its pKa is 5. Yep. What about this cyclopentane? What's its pKa? About 50. Good. It's an alkane. What about this one, the nitrogen with the lone pair and 3 bonds? $35. Good. And then the hydrochloric acid, -7. Yeah. And then the alcohol here, 16-ish. And then once you've had all those out there, I said, put the word wimpy by the weakest acid. So that would be the alkane, pK 50, and that was all I asked. Okay. The strongest acid is the hydrochloric in this case. And then I asked you to draw in, okay, I'll do this one for you. I got a lot of questions on this one. You know, I was saying before to read a question, then read it again, and then do it, and then read to make sure you did it. Make sure you do read this over after you've done it so you didn't miss anything. A lot of steps to this question. I'm trying to really narrow you in on this. So let's try this. Boom. Oh, I'm making it a little too big. Okay. So I'm going to draw in my reacting electrons with color. I'm waiting for my Jamboard to get going. Let's go, Jamboard. Okay, here we go. So I'm going to add color, like the nitrogen is going to be the base here. I'm going to make that have a red pair of lone pair electrons, and then the sulfuric acid is going to be the acid. Let's go like this. So let's work this out. My amine is going to come over, deprotonate this, and then break the bond between the hydrogen and oxygen like that. And my product will be 1, 2, 3. Oxygen. And this is the sulfuric acid becomes hydrogen sulfate. And see, I'm doing really good with my formal charges, right? The way you check your formal charges in this thing is you say the products, formal charges all should add up to be the same as the reactants. So my reactants have 0 formal charge, 0, so overall 0. Products, I got a +1 and a -1, overall 0. Looks good. And another thing that's probably a good idea to do, I'm going to number my carbons like 1, 2, 3. Did I get all those? 1, 2, 3. Looking good. Okay. And now, is this product a reactant favorite? I got to find the reactant side acid. Which one's the reactant side acid? Is it this amine or the sulfuric acid? The sulfuric acid, huh? Reactant side acid, pKa is what? Does anybody remember? -10, yeah. Okay, and then on the product side, which would be the acid if it reverses? Is it the ammonium or the hydrogen sulfate? Yeah, product side acid. because to reverse the reaction, the hydrogen sulfate has to deprotonate it, like that. Okay, so what's the pKa of an ammonium? Is it the -9? Is it the 9 or the 35 one? It's the 9 one because it has 4 bonds and a plus charge. Okay, cool. So right off the bat, who's the stronger acid, sulfuric acid or ammonium? Yeah, stronger acid, lower pKa. So that's the stronger acid. Which one, if it's the strongest acid, is this product favorite or reactant favorite? Product favorite. And so let's calculate how product favored. Let's calculate K equilibrium. It's 10 to the product side, pKa 9, minus the reactant side, which is -10. So it's 10 to the 19. Whew. Very, very product favored, right? 10 with 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Might have missed some. So it's that many times product favored. So extremely product favored. So this would be a reaction, you got to be careful, like it'll be exothermic and very exothermic. So if you're to react these, you want to go real slow and you mix them. If you mix them together too fast, it might like explode on you. So that was one example. Here's another one, and there's another one. And the answer keys are given for these too. So I just answered some of those, but the rest of them are here. There we go. So that's the quiz you'll take. All right, so and this topic, I spent a lot of time on it. Like I have today's lecture because I want you to get to the point where you don't even have to like write out all the answers. You could just quickly look and say things like, oh yeah, -2, minus a -7. Oh, this is going to be product favored. Let's see where we're at. So we got it. We're good on that. Before I do outcome 9, let me go back to 1. And these outcomes, oh, the reaction coordinate diagrams. I'm going to do just outcomes 1 and 2. Right now, we'll end that off for today. Then we'll pick up on outcome 3 on Monday. So let me get back to this. Okay, so thermodynamics versus kinetics. We can describe reactions and talk about them and use these concepts to predict things about them in terms of their thermodynamics and kinetics. So thermodynamics is just looking at the energy change throughout a reaction, like, oh, my reactants are higher in energy than my products, or my products are higher in energy than my reactants. So thermodynamics just looks at the reactants before they react and the products after they react. It doesn't look in between. And we use the thermodynamic quantities like equilibrium constants. They're a thermodynamic thing, not a kinetic thing, equilibrium constants, because in equilibrium constants, we're looking at concentration of products over concentration of reactants. And like the Gibbs free energy change of a reaction, that's thermodynamics. And when you say a reaction is exothermic or endothermic, that's thermodynamics. It's just looking at reactants products. And now in the relationship between the energy that takes place, those is like, the idea is if you break a bond in a reaction, it takes energy. And when you make bonds, you release energy. We'll see this make more sense in reaction coordinate diagrams, but I think we talked about this earlier in the semester too. So, okay, thermodynamics. I know there's a lot in this, and we're going to be going over this idea a lot throughout the year, so it'll stick good. So we got that one, and then so kinetics now. is different in that for kinetics, you're looking what's happening between reactants and products. So when we do the curved arrow mechanisms, that's like looking at kinetics. We're seeing how the reaction takes place. And it's also related to the speed of the reaction. So when we say a reaction's fast, that's kinetics, or slow, it's kinetics. Reaction that's product favored is usually fast, but not always. Like turning coal or diamonds to coal, I think that's product favored, but it's really, really slow. Or is it the other way? Coal to diamonds? I forget. I should look it up. All right, so it depends on the energy that takes place between reactions and product, the kinetics. And we'll talk about this thing called activation energy. Have you heard of activation energy in general, Chem? Yeah, so the activation energy is just the minimal amount of energy that it takes for two atoms to react. So for two atoms to react, they need to collide, and they have to collide with the correct orientation and with enough force. So if the two atoms collide correctly, but super slow, they just bounce. But if they collide hard enough, then they can react. So that the energy involved with that is activation energy. They have to collide with enough energy to equal their activation energy. And then we got rate law, rate equations. Yeah, and I got the two molecules. So let me see what time we got. Let's do one quick reaction coordinate diagram. That'll help all these just words make more sense. Getting my Jamboard caught up here. We'll just do a simple acid-base reaction again. So let's do, what kind of acid? Someone name one of our acids that we've memorized the pKa of. We did sulfuric acid before, or did we? Yeah, we just did the last example. Let's give another one. We haven't done a carboxylic acid, have we? I don't think so. Let's do a carboxylic acid. I know I asked you and then I just denied you, sorry. Thank you for playing. Okay, I'm gonna do sulfuric acid. And what do we want it to react? Give me a base, any base. Okay, hydroxide it is. Okay, here's our mechanism. The hydroxide will reach out a pair of electrons, these red ones, make a bond to that hydrogen, and then break the bond between the oxygen and the hydrogen. And it will produce carboxylate. And water. Did my charge balance in this reaction? I have a minus charge hydroxide, no charge on the carboxylic acid, minus charge carboxylate, no charge on the water. Yeah, it balanced out. And then our carboxylic acid has resonance, huh? So the resonance arrows, you can draw them like this. Just like that, right? Cool. So we've got resonance structures, double-headed resonance arrow. There we go, we got a reaction. Is this product favored or reactant favored? So is it product favored or reactant favored? Product favored. And that doesn't always mean it's a exothermic, but this one, it's also exothermic. I'll just tell you that up front. Okay, so I'm gonna quickly do the reaction coordinate diagram, and I'll do more at the start of next lecture. So the way we do these is we draw an axis with energy on one side and then something we call reaction coordinate down here. Reaction coordinate is kind of like the time that the reaction takes place. So you start with the reactants on the left. So here's my reactants, and I draw a line to represent their area. I mean, their energy that they start at. So let's say I have my carboxylic acid here and the hydroxide. These two molecules have to collide together to react. Oops, delete it. And they have to collide with enough energy. So they have like, we're gonna represent their energy with a curve like this. They're gonna collide with enough energy to overcome what's called the activation energy to get to the transition state. So that's the transition state there. They have to collide with enough energy to overcome that. And then their products, they're exothermic, so we'll draw them lower in energy than the reactants. So they'll come down, they'll become these reactants, the products there. This energy here, going from reactants, lowest energy to the transition state, that's the activation energy. Okay. And that's pretty much it, except for I'll add a couple more things here. This is you could see, because if you start here and you go to there, there's this, it went down in energy, huh? So the reaction is exothermic. It's releasing heat. And I can draw the transition state real quick. We're gonna practice this. I'll just finish with this guy right here. Let's draw it. Drawing the transition state is real helpful to understand these reactions, and I'll have you do it with more and more detail as we learn more about this. You draw the bond that's breaking with dots and the bond that's forming with dots too. And then we add partial charges. So this bond, the carbon, this oxygen of the carboxylic acid, it's going from having 0 charge to negative charge. So in the transition state, it's partial negative. And I'll do it here. So if you look at the overall reaction here, we go from the oxygen here being no charge to being negative charge. So it's in between like 0 and -1. So it's partial negative. And then the hydroxide starts off negative, and it becomes neutral. So it's going from like -1 to 0. So it's also partial negative. Oh. So that's the first energy versus reaction coordinate diagram you're seeing. And I don't expect you to right now fully grasp all of this, but we're going to do lots and lots of these all year. So you'll get better at them. And next lecture, I'll start with one. I might start with one in the lab too. Maybe I'll do an entrance question with one of these. That'll be good. Okay, so, oh, and then I don't think I really explained it well, but the transition state is what we imagine the molecules look like at their highest energy between reactants and products. So this is kind of what we guess the molecule looks like, because we can't really isolate this. We can just guess, because it seems to make sense if we have these reactants and these products that it looks like that. And we know that these two molecules have to collide with enough energy, the activation energy, in order to react. If they collide with less than this, like say they collide, but they only collide with that much energy, then they just come back. So they're going back and forth. And then when they get hit hard enough, oh, now I can react and I could come this way. All right. So that'll cover it for today. Monday, I'll do more of these reaction coordinate diagrams and